GISP Unofficial Study Guide, Section 9, Systems Design and Management. Section 901, Knowledge of Systems Architecture and Design, including various GIS softwares, platforms, and environments. Architecture Design. Architecture design includes the requirements phase, the design phase, the construction phase, implementation phase, and capacity planning tool, or CPT. Requirements phase includes a user needs assessment and workflow loads analysis, including a baseline and peak traffic measurement. The design phase includes infrastructure requirements, network communication capacity, hardware and software procurement, software development, and data acquisition must be identified. The construction phase includes system procurement, data acquisition and database design, authorization for application design and development, and prototype testing. The implementation phase includes initial deployment and operational testing, final system delivery, user training, and system maintenance operations. The capacity planning tool was developed as a framework to promote successful GIS system design and implementation. The architecture design process includes requirements phase, design phase, construction phase, implementation phase, and the capacity planning tool, or CPT. Enterprise environments. The enterprise GIS environment is a broad spectrum of technology integration of enterprise technologies connected by local area networks, wide area networks, and internet communications. Enterprise technologies. Enterprise technologies include database servers, storage area networks, Windows terminal servers, web servers, map servers, and desktop clients. Platforms. Different platforms for GIS include a desktop, which is an individual user on a computer making maps, doing data analysis, and data creation. A server. A server brings GIS into the hands of everyone in the organization, allows access to WebGIS, control of GIS data on your own infrastructure, control over how GIS platform is deployed, maintained, secured, and used. Being hosted in the cloud gives GIS the ability to discover, use, make, and share maps with any device, anywhere, anytime. Gives access to other users, the maps and data that you produce, and connects more people outside of the organization to share the latest maps, data, and ideas. And enterprise GIS. An enterprise GIS is integrated throughout the entire organization so that a large number of users can manage, share, and use spatial data and related information to address a variety of needs, including data creation, modification, visualization, analysis, and dissemination. An enterprise GIS can utilize both hosted in the cloud and server, but if the organizational data is not stored in the cloud and only data is accessed from the cloud, then it is not quite an enterprise system. Software. Software runs on a variety of hardware types. GIS software can run on centralized servers or desktop computers. The software may rely on the database management type, a database management system type, or the operating system type. System infrastructure can include hardware, software, and a communication network. It includes required information about products and spatial and non-spatial data resources. Essential spatial analysis, display, and reporting functions, data management resources, and the anticipated number of end users within the department. Virtualization is the creation of a virtual machine that acts like a real computer with an operating system. Types of GIS software include GRASS, which was developed by the U.S. Army Corps of Engineers. It's open source. Esri, which produces ArcMap and ArcGIS Pro. QGIS, MapInfo, and SmallWorld. System design strategies. System design strategies. The components of system design include the system design process, GIS software technology, software performance, server software performance, GIS data administration, network communications, platform performance, information security, GIS product architecture, performance management, system implementation, the capacity planning tool, the system design process. The system design methodology includes identifying business requirements, making appropriate software selection, using properly configured data sources, and providing sufficient hardware to meet the user productivity needs. The GIS should be built with performance and scalability to perform during peak operational loads. System architecture design. System architecture design is a process developed by Esri to promote successful GIS enterprise operations. This process builds on your existing information technology infrastructure and provides specific recommendations for hardware and network solutions based on existing and projected business or user needs. System design starts with identifying business needs. This includes identifying user locations and required information products, identifying required data resources, and developing appropriate software applications to do the work. Business needs are represented by project workflows that identify the traffic and processing associated with each display transaction. System architecture design translates business needs to identified IT requirements. Hardware requirements are generated based on peak software processing loads. Network connectivity requirements are generated based on peak data flow. Capacity planning tools are provided to automate the design analysis. System performance is limited by the weakest link in system design. System architecture design identifies the weak links during the planning process and promotes investment in a balanced system design. A distributed computer environment must be designed to properly support user performance. The weakest link in the system will limit performance. The primary reasons for planning include identifying business needs, defining project requirements, and reducing implementation risk. A traditional system design process starts with a GIS needs assessment. The GIS needs assessment includes a review of user workflow requirements and identifies where GIS technology can improve the quality and productivity of the business process flow. System architecture design. The system architecture design is based on the user requirements identified by the GIS needs assessment. Customers must have a clear understanding of their GIS application and data requirements before they are ready to complete their system architecture design. Building a GIS implementation strategy. There are several critical deployment stages that support a successful implementation. The implementation strategy includes the processes, the requirements phase, the design phase, construction phase, and implementation phase. During the requirements phase, the user information product needs establish a foundation for completing the design. The user location and peak business loads establish a foundation for system architecture design. The design phase includes infrastructure requirements must be identified to quantify deployment costs. Network communication capacity is an important consideration for GIS deployments. Hardware and software procurement requirements must be identified. Software development and data acquisition must be identified. During the construction phase, the construction phase includes system procurement authorization based on the design budget and deployment timeline. Data acquisition and database design efforts begin. Procurement authorization for application design and development. Prototype testing plans completed and scheduled to validate product delivery within design performance targets. The implementation phase consists of the initial deployment and operational testing, final system delivery, user training, and workflow migration complete. It also includes system maintenance operations. The building a GIS implementation strategy includes requirements phase, design phase, construction phase, and implementation phase. System performance terminology. A workflow transaction is an average unit of work. A throughput is a measure of the transaction rate. Capacity is the maximum rate at which a platform can do work. Utilization is the percentage of capacity represented by a given throughput rate. The system architecture design process. The enterprise GIS system design process aligns identified business requirements or user needs derived from business strategy, goals, and drivers or business processes with recommended business information systems infrastructure technology, network and platform recommendations. The system architecture design process includes a user needs assessment, a workflow loads analysis, a technical architecture strategy, a user requirements analysis, a network suitability analysis, platform architecture selection, software configuration, and enterprise design solution. A user needs assessment The results of a GIS user needs assessment provides inputs for the system architecture design analysis. The workflow loads analysis translates user needs to project workflows with baseline traffic and processing transaction loads based on estimated workflow complexity. Technical architecture strategy identifies user locations, network connectivity, and data center server locations. The user requirements analysis translates peak user workflow loads to peak throughput transaction loads. The network suitability analysis translates peak site network throughput loads to peak site network traffic and compares with available network bandwidth. The platform architecture selection identifies data center platform tier configuration and identity platform selection for each tier. The software configuration identifies platform assignment for each workflow software component with peak transaction processing load. The enterprise design solution combines all peak workflow software component processing loads on the assigned platform tier, translates baseline processing load to selected platform processing load, and generates the number of nodes required for each platform tier with the estimate of capacity utilization. The Capacity Planning Tool. The Esri Capacity Planning Tool was developed to simplify business requirements data collection and automate system design analysis tasks associated with each phase of the development cycle. A batch process. A batch process is a workflow that does not require user interaction. Most heavy GIS analysis can be modeled as batch processes. GIS software technology. Since the early 1970s, Esri has continued to develop GIS software technology supporting functional requirements identified by the GIS user community. Software development history gives us insight into the basic principles that guide us in building the technology of the future. Tightly scripted software code. The early ArcInfo software provided developers and professional GIS users with a rich toolkit for geospatial query and analysis and demonstrated the value of GIS technology. Object relational software. Hardware performance improvements led to more efficient programming techniques deployed in the late 1990s. Service-oriented architecture. Web technology introduced more ways to share data and services, introducing a services-oriented component architecture along with the interoperability standards that enable open and adaptive applications developed from multi-vendor component architecture. Cloud computing platform architecture. Hardware virtualization, data center automation, and self-service cloud computing provide simpler ways to administer and support GIS applications and services. Distributed operations. ArcGIS Enterprise, WebGIS, and Enterprise Solutions provide support for hybrid distributed operations. Four different types of GIS: traditional GIS, centralized GIS, GIS online sharing, and WebGIS architecture. Traditional GIS. Professionals in GIS departments develop and maintain data sources and create geographic information products from their local work environment. GIS users request maps prepared by GIS analysts for use in their work. Departments throughout the enterprise establish their own local GIS groups for building and managing operational level geographic content. GIS data is distributed as files, such as shapefiles, file-based geodatabases, personal geodatabases, SQL Express, and accessed locally. Centralized GIS. In centralized GIS, GIS data is developed and maintained in a centralized geodatabase shared by all departments through the enterprise. The enterprise application workflows are established with direct user access to dynamic geographic information products used in their work. GIS data resides in centralized enterprise geodatabases hosted by relational database management systems. GIS online sharing. ArcGIS Online shares a selection of common cloud-hosted, cached base maps and imagery that GIS users can share across a wide area network. These files can be shared and downloaded to be viewed or analyzed using local GIS desktop software. WebGIS architecture. ArcGIS Online organization services extended GIS user access to directly create and share geospatial data services to users on any device at any location through the cloud. Direct access to dynamic geospatial data services, configurable applications for web and mobile phone clients, and real-time geospatial data feeds over a wide area network. GIS information products are published as dynamic, REST-based, loosely coupled data services that can be consumed by all GIS applications, desktop, web, or mobile. ArcGIS Enterprise. The ArcGIS Enterprise deployment concept, managing information from a community of services, and delivering web maps to applications supported on every device. The ArcGIS portal is a content management enables customer engagement, collaboration, and sharing, which empowers business users to create and share content. Integrated platform architecture facilitates information, development, and sharing. ArcGIS desktop clients create and publish services. GIS content can be published and shared from server, online content, and internet services. Web maps can be developed by end users for analysis and collaboration. Access and identify management can be managed by the end user community. GIS information products can be accessed as a service and shared on any client application. The Capacity Planning Tool, or CPT. The Capacity Planning Tool was developed to automate the system design process by Esri. The CPT is an Excel workbook designed as a model to configure business requirements and generate appropriate platform design solutions. Microsoft Excel functions are used to automate the design analysis and identify a design solution that satisfies identified business requirements. Platform performance. Moore's Law. Intel founder Gordon E. Moore released a paper in 1965 that predicted the number of components in integrated circuits would be doubled every year through at least 1975. His prediction, known as Moore's Law, was proven true for over 50 years, and processor design improvements continue to contribute to computer performance gains. Faster platforms provide more service with less hardware. Information security. Information security is the process of protecting the availability, privacy, and integrity of data. Types of security threats. The CIA security triad. The core principles of information security management are represented by the CIA triad. The CIA triad includes confidentiality, integrity, and availability. Confidentiality is protection of privileged communications, restricting user access to core business information based on a need-to-know principle. Integrity refers to the trustworthiness of business data resources and associated information products generated over its entire life cycle. Availability refers to ensuring the information system is functional when needed to support operational business requirements. Security needs for every organization are unique. More security will result in a higher level of security investment, higher increases in complexity and system costs, restricts access to data sources and online services, eliminates external online collaboration, prevents most connected mobile applications, and provides optimum protection to manage security risks. Basic security requires minimum level of security investment, enables the simplest and lowest system cost, enables full access to internet data sources and online services, provides optimum business environment for external collaboration, extends enterprise operations to include connected mobile applications, and protects the system from internet virus attacks. Virtualization. Virtualization is the act of creating a virtual, rather than actual, version of something at the same abstraction level, including virtual computer hardware platforms, storage devices, and computer network resources. Hardware virtualization or platform virtualization refers to the creation of a virtual machine that acts like a real computer with an operating system. Software executed on these virtual machines is separated from the underlying hardware resources. For example, a computer that is running Linux may host a virtual machine that looks like a computer with the Microsoft Windows operating system. Windows-based software can then be run on the virtual machine. Different types of hardware virtualization include full virtualization, where almost complete simulation of the actual hardware to allow software environments, including a guest operating system and its apps, to run unmodified. Para-virtualization is when the guest apps are executed in their own isolated domains, as if they are running on a separate system, but a hardware environment is not simulated. Guest programs need to be specifically modified to run on this environment. Section 902, Knowledge of Systems and Application Security. Application security consists of making applications more secure by finding, fixing, and enhancing the security. Application security is important because it will keep the data safe. Continuous deployment and integration cause security fixes to be deployed constantly, daily or hourly. Security testing includes static testing. Static testing analyzes code at fixed points. Dynamic testing analyzes running code and can simulate an attack. Interactive testing combines static and dynamic testing. Mobile testing is designed to examine how an attacker can attack mobile apps. Methods to prevent unauthorized access to data and metadata include define who has access, use other software to enforce these policies, identify management systems to check the credentials of users, and data authenticity verification. Application security. Application security, for short AppSec, includes all tasks that introduce a secure software development lifecycle to development teams. Its final goal is to improve security practices and to find, fix, and preferably prevent security issues within applications. It encompasses the whole application lifecycle from requirements analysis, design, implementation, verification, as well as maintenance. Security threats. The Open Web Application Security Project found the top 10 most critical web application security risks include broken access control, cryptographic failures, injection, insecure design, security misconfiguration, vulnerable and outdated components, identification and authentication failures, software and data integrity failures, security logging and monitoring failures, and server-side request forgery. Section 903. Awareness of trends in geospatial technology. Be aware of where GIS is heading. Read blogs, attend conferences, attend webinars, join local and online GIS groups, observe job postings for skills required, review LinkedIn profiles of similar GIS professionals. Current and upcoming trends in geospatial technology include artificial intelligence in GIS data creation, machine learning in GIS, IoT, the Internet of Things, drones, and mobile field data collection. Examples of artificial intelligence in GIS. FedEx's global logistics operation relies on extreme position. To keep planes and deliveries on time, FedEx uses a sophisticated GIS to track its fleet. That GIS is augmented with AI's predictive capabilities to identify when a plane would need parts or maintenance, making a complex supply chain even more efficient and on schedule. The Internet of Things, IoT. The Internet of Things describes devices with sensors, processing ability, software, and other technologies that connect and exchange data with other devices and systems over the Internet or other communications networks. The Internet of Things encompasses electronics, communication, and computer science engineering. The Internet of Things has been considered a misnomer because devices do not need to be connected to the public internet, they only need to be connected to a network and be individually addressable. The main concept of a network of smart devices was discussed as early as 1982 with a modified Coca-Cola vending machine at Carnegie Mellon University became the first ARPANET-connected appliance, able to report its inventory and whether new loaded drinks were cold or hot. The Internet of Things has been defined as simply the point in time when more things or objects were connected to the Internet than people. Cisco Systems estimated that the Internet of Things was born between 2008 and 2009, when the things-people ratio growing from 0.08 in 2003 to 1.84 in 2010. 5 tech trends driving new geospatial development. 1. The real-time revolution. Although real-time spatiotemporal data is now being generated almost ubiquitously, and its applications in research and commerce are widespread and rapidly accelerating, the ability to continuously create and interact in real time with this data is a recent phenomenon. 2. Miniaturization of technologies. The capacity to create small and often inexpensive devices and sensors with wireless connectivity is driving an explosion of the Internet of Things. Miniaturized and lower-cost sensors lead to an increase in what, when, where, and how much data is collected, and, more importantly, the ability to attune the sensor to the specific data collection needed. 3. The proliferation of new mobile geospatial sensor platforms. The rapid miniaturization of technologies has made it feasible to explore new modalities for sensor distribution, such as small satellites and unmanned aircraft systems, that can be rapidly designed and deployed with orbits or flight paths tailored to the mission. These mobile geospatial sensor platforms greatly expand the abilities of individuals, businesses, and governments to collect volumes of remotely sensed data. 4. Expanding wireless and web networks. Faster and broader wireless and web networks are beginning to address, in part, the growing demand for improved methods of data transmission and geospatial data distribution to end users. This is laying the groundwork for governments and consumers around the world to more broadly share and use spatiotemporal data, including for real-time apps. 5. Advances in computing capacity for geospatial research. High-performance computing networks and cloud computing services are providing governments and others with conduits through which they can more easily and quickly access and contribute to growing repositories of geospatial data, tools, and services.